Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1, you can see, has 4 different parts to it. The first part asks, what is the empirical formula of naphthalene? Part 2, the empirical formula of acetic acid is CH2O. If its molar mass is 60.05, what is the molecular formula? Part 3 is also looking for its empirical and molecular formulas. And lastly, we are given percent compositions of both carbon and hydrogen. And then we just need to find its empirical formula. Okay, so let's just tackle all the different questions one by one. So part A is pretty easy. What is the empirical formula of naphthalene? Okay, so let's just write down the definition of empirical formula in case you didn't know what it meant. Okay, so empirical formula is basically just the simplest ratio of atoms. So the opposite of the empirical formula would just be the molecular formula. So in the case of naphthalene, the molecular formula is C10H8. So if we wanted to find its empirical formula, we would just need to write C10H8 into the simplest ratio. So notice that both 10 and 8 are divisible by 2. So the empirical formula would just be C5H4. And that is the answer to the first part of question 1. So the second part gives us the empirical formula, CH2O. And it also gives us the molar mass, which is 60.05 grams per mole. What is the molecular formula of acetic acid? So we can break this up into different steps. So step 1 is to find the mass of your empirical formula. So if we know the mass of our empirical formula, we can find out its ratio with the molar mass that's given, and then we'll know whether or not, like, how to multiply in order to get our molecular formula. So first, we need to find the empirical formula mass. So the empirical formula is CH2O, and I just denoted it as a capital M, like molar, like as if we're finding the molar mass of CH2O. So it would be the molar mass of carbon plus 2 times the molar mass of hydrogen plus the molar mass of oxygen. So the molar mass of carbon, so these values are just found on the periodic table, and it is 12.01 grams per mole. For hydrogen, it's 1.01 grams per mole. And for oxygen, it's 15.99 grams per mole. So the empirical formula mass is 30.02. Okay, so step 2 in answering this question, what did I just say? Answering this question is to find the ratio between the empirical formula mass and the actual molar mass, which is 60.05. So let me just show that I'm going to divide our actual by our empirical. Actually, I'll write this as molecular over empirical. So the actual molar mass was 60.05. And the empirical formula mass is 30.02. So when we find the ratio, we want to just round to the nearest whole number. So in this case, it would just be 2. So now for step 3, we just need to multiply by the ratio. So our empirical formula mass was CH2O. Multiplying this whole thing by 2 gives us C2H4O2. And then this is our molecular formula. Okay, so that is part B of the first question. So I'm going to start a new page and do part C. Isoprene is a liquid compound that can be polymerized to form natural rubber. It is composed of 88.17% carbon and 11.83% hydrogen. Its molar mass is 68.11 grams per mole. What are its empirical and molecular formulas? So this is pretty much taking what we already know, and it makes it a little bit more difficult. But again, I'll just break it down into different steps. So step 1, since they give us the percent composition of the sample, the first thing I like to do is to assume we have 100 grams of sample of isoprene. So this makes it easy for us to convert from percentages to grams. So if we had 88.17% of a 100 gram sample of isoprene, this gives us a mass of carbon to be equal to also 88.17 grams. And similarly with hydrogen, this gives us 11.83 grams. Okay, so now that we have the masses, the second step is to find the number of moles. So let's recall the equation for number of moles is mass over molar mass. So first, let's look at the carbon. Its mass was 88.17 grams. And the molar mass of carbon is 12.01 grams per mole. Okay, so the number of moles of carbon is 7.3. So now let's do the same thing for hydrogen. Its mass is 11.83 grams, and the molar mass of hydrogen is 1.01 grams per mole. So this gives us number of moles equal to 11.8. Okay, so now that we have the number of moles of both, we want to divide by the smallest. So our smallest value was 7.3, and that is for carbon. So let me just show here that we divide both values by 7.3. And then when you divide 11.8 by 7.3, we are just going to round to the nearest whole number, and we end up with C1H2. So this is our empirical formula. So that answers the first part. We can also we don't even have to write the 1. It'll just be CH2. Okay, so the question also asks for the molecular formula of isoprene. So this brings us to step 4, which is to just find the empirical formula mass. So now this is similar to the previous part of this question. So I'm just going to write molar mass of CH2 is equal to 12.01 plus 2 times 1.01, and its mass is around 14.03. Okay, so now let's look at its actual molar mass, which is 68.11. So now we just have to find the ratio. So 68.11 divided by 14.03. Again, we want to round to the nearest whole number, which is 5. So now, if we multiply our empirical formula by 5, we end up with C5H10. Okay, so CH2 was our empirical, and then C5H10 is our molecular. And now let's answer part D. I'll also start a new page again. Camphor is found in camphor wood, much prized for its wonderful odor. It is composed of 78.90 grams of carbon and 10.59% hydrogen. The remainder is oxygen. What is its empirical formula? This is similar to the previous part, but they need us to find the percentage of camphor that is oxygen. So step 1 is to again assume 100 grams of camphor. If 78.9% of camphor is carbon, then the mass of carbon in 100 grams is 78.90 grams. And the mass of hydrogen is 10.59 grams. This means that the mass of oxygen is equal to 100 grams, subtract 78.9, and then subtract 10.59 grams. And this gives us the mass of oxygen, which is 10.51. Okay, so now we have the masses of all of our atoms. Now we have to find the number of moles. For carbon, it is 78.9 divided by 12.01. Okay, so this gives us 6.57. For hydrogen, it's 10.59 divided by 1.01. And you end up getting 10.48. And then lastly for oxygen, 10.51 grams divided by the molar mass of oxygen, which is 15.99. So this will give us 0.65. Okay, so now that we have the number of moles of all of them, we want to divide by the lowest number of moles. So let's show C. So the lowest number was 0.65 moles. So for carbon, it's going to be 6.57 divided by 0.65. For hydrogen, it's 10.48 divided by 0.65. And then for oxygen, it's just 0.65 divided by 0.65. Okay, so again, we're going to take all the different fractions and convert it to the nearest whole number. And we end up getting C10, H16, and then O. And this is our empirical mass. Okay, so that's where this question ends up, because they don't ask for molecular, nor do they give us the molar mass of camphor. So this question is done. And now we can compare our answer with the junior tutor. So starting all the way back to part 1A, the empirical formula of a compound gives the simplest ratio of the number of different atoms present, whereas the molecular formula gives the actual number of each different atom present in a molecule. Dividing the subscripts by 2, the empirical formula of C10H8 is C5H4. Okay, so part 1 is correct. To determine the molecular formula given the empirical formula, first divide the molar mass of the compound by the empirical formula mass. The result should be a whole number or very close to a whole number. Then multiply all the subscripts in empirical formula by the whole number found previously. The result is the molecular formula. So they found the empirical formula mass to be 30.026. Dividing it by the molecular, you get 2. And then they found their molecular formula to be C2H4O2. Okay, so part 2 is correct. Part 3, first find the empirical formula by doing the following. Get the mass of each element by assuming a certain overall mass for the sample. And then they say 100 grams is a good mass to assume when working with percentages. Okay, so then they just showed how you would get the masses. They got 88.17 grams and 11.83 grams. Convert the mass of each to moles, so 7.3 and 11.73. Divide each by the smallest value to get the subscripts. So here they showed that when you divide, you get 1.6, but then they round to the nearest whole number, which is 2. And then they found the empirical formula, which is CH2. To get the molecular formula, determine the mass of the empirical unit. So it was 14.03. Next, determine how many empirical units are present in the molecular unit. So again, they got around 4.856, but then they rounded it to 5. And they found their molecular formula to be C5H10. And now let's look at the last part. Similar process as in number 3 to be carried out. Okay, so they showed how to find all the number of moles. For carbon, 6.57, hydrogen, 10.5-ish, and then for oxygen, 0.65. Dividing by the smaller value, we get 10, 16, and 1, and their empirical formula is C10H16O. Yep, so this solution is correct. Okay, so that was a long multi-question question number 1. And now we can just move on to question number 2. How to determine the coordination number in transition metal complexes. So let's just first write down the definition of a coordination number. So basically, we want to just count all the ligands that are attached. That's not how you spell attached. Attached to the metal center. Okay, so it's pretty easy enough, but let's just have an example. Let's say we had copper as our metal center, and it is coordinated with chlorine atoms. Okay, so now we just need to count how many ligands this copper has. So by ligands, that just means like the groups that are attached to it. And I count 4 chlorine atoms. So therefore, the coordination number for, and then this is copper 2+, And we know this because each chlorine atom is negatively charged, has a -1 charge. And if the overall complex has a -2 charge, that means copper has a +2 charge. So the coordination is 4. Okay, so let's just see what our junior tutor said. The coordination number can be determined just by counting the ligands that are attached to the transition metal central atom in a complex. Yep, so this solution is correct. Okay, so question 3. Which among the following salts are acidic, basic, or neutral? Okay, so first let's just find out what makes each salt an acid or a base or neutral. I'm just going to write all the different types of salts. When you have an acidic salt, this is made from a strong acid plus the salt of a weak base. When you have a basic salt, this is when you have a strong base that was reacted with the salt of a weak acid. And lastly, when you have a neutral salt, this was made from a strong acid reacting with a strong base. Okay, so now that we know all these types of salts, let's look at the different options that they give us and try to figure out what type of salt it is. Okay, so first we have this lithium chlorous acid. So this was made from lithium hydroxide, which is a strong base. And I believe this is hypochlorous acid, which is strong. So therefore, this salt is neutral. Next, we have potassium phosphate. So this was made from H3PO4. So this is a weak acid. And the potassium is formed from potassium hydroxide, which is a strong base. So therefore, this is a basic salt. Next, we have ammonium bromine. So this was made from HBr, which is a strong acid, and ammonium hydroxide, which is a weak base. So this is an acidic salt. Next, we have potassium chloride. So this was made from potassium hydroxide, which is a strong base, and hydrochloric acid, which is a strong acid. Therefore, this salt is neutral. And then lastly, we have sodium fluoride. So this was made from hydrofluoric acid, which is weak, and sodium hydroxide, which is a strong base. So therefore, this is a basic salt. Okay, so these are all the different types, and let's see what the junior tutor said. There are several rules that govern the acidity, basicity, or neutrality of a salt. These are the following. 1. Salts of a strong base and a strong acid are neutral. Salts of a strong base and weak acid are basic. Salts of a weak base and strong acid are acidic. And salts of a weak base and a weak acid is dependent on the Ka or Kb value. Whichever is higher will determine its acidity and basicity. To answer the question, this one's neutral. Salt of a strong base and strong acid. A3PO4 is basic since it's a salt of a weak acid and strong base. And ammonium bromide is acidic since it is salt of a weak base and a strong acid. Potassium chloride is neutral since it's a salt of a strong base and strong acid. Lastly, sodium fluoride is basic since it is a salt of a weak acid and a strong base. Yep, so this solution is correct. Okay, so moving on to question number 4. How do enzymatic catalysts increase the rates of reactions? Okay, so first let's write down the role of catalysts. Basically, they lower the activation energy of a reaction. So I'll just denote activation energy by EA. And catalysts also promote the formation of a transition state. Okay, so as you can guess, transition state is pretty much transitioning from your reactant to your product. Okay, so I'm just going to show how catalysts can affect the reaction by drawing a free energy diagram. So the x-axis is the reaction progress. And our y-axis is the free energy. Okay, so in red, this is typically what an uncatalyzed reaction looks like. So I'll show that our reactants start here at the beginning. And you can see that the gap from here to here is very long. And this is the activation energy. So you can see it takes a lot of energy for the reactants to convert to the products. But when we have a catalyzed reaction, which I'll show in green, it lowers this activation energy to make the reaction happen a little faster. So this will be catalyzed. And you can see that the activation energy is decreased. Okay, so that's how catalysts work. And the junior tutor said, catalysts in a reaction increase the rate of reaction by lowering the activation energy. Enzymes are biological catalysts that speed up reactions by lowering the activation energy. Thus, less energy is required for the substrates to reach the activation energy to transform it into its transition state, then finally into products. Enzymes promote the formation of the transition state by bringing substrates together to form an enzyme-substrate complex on a particular region of the enzyme called the active site. Yep, so the solution is correct. Okay, so now let's move on to question number 5. Okay, so it says, given this chemical equation, if the initial concentration of all the reactions is 2 moles per liter, answer the following questions. What is the Kc expression? And fill in the ice table for this reaction. What are the concentration of each of the gases at equilibrium? Okay, so first let's write down the chemical equation. We have carbon dioxide reacting with H2O gas to form, we started off with carbon monoxide to form CO2 gas plus hydrogen gas. Okay, so first let's make sure that the reaction is balanced. We have 1 carbon on each side, 2 oxygens, and 2 hydrogens, so everything is already balanced. And now we can just construct our ice table. So since none of these compounds are solids or gases, they will all be included in the ice table. So they gave us the initial concentration of all the reactants, which is 2 moles per liter. So both water and carbon monoxide will put 2.00 under its initial concentration. And the initial concentration of our products, obviously we both just have 0. Okay, so moving on to the change for both the reactants, it changes by -x, and for our products, it changes by +x. And we know this because as a reaction progresses, we start to lose our concentration of reactants, and we start to gain more concentration of the products. And now we write the equilibrium expression, which would just be 2 minus x. And then our products will just be equal to x. Okay, so now I'll write down the expression of Kc, which is our equilibrium constant, concentration constant. So this is found by multiplying the concentration of our products. So our products are CO2 and H2, and it's going to be divided by the concentration of our reactants, which is carbon monoxide and water. So the question gave us the Kc value, which is 3.80. And instead of writing the concentrations, I'm going to write the expressions we found for all of them from the previous ice table. So if we have the concentration of CO2 and H2 both equal x, when you multiply it together, you get x squared. And then for the denominator, it's going to be 2 minus x times 2 minus x. Okay, so now we get this quadratic kind of like expression. Let's try to simplify it and try to solve for x. So the goal is just to write this as a quadratic equation so that we can plug it in to the quadratic formula and solve for x. Okay, so this is just using some high school math. First, outside, inside, last gives us 4 minus 4x plus x squared. And then simplifying this some more, let me bring this up here. You should end up with 2.8 x squared minus 15.2x plus 15.2 is equal to 0. And now just by using the quadratic equation, or you can use like a quadratic equation calculator if you looked it up. We want to get the x, like typically we want to get an x value that is the positive number. But you'll notice that when you find the value, the two values of x that you would get if you solved this equation, you'll notice that both of them are positive. So the x value that you want is going to be less than 2. And we know this because if it was greater than 2, then we would get a negative concentration when plugging it into 2 minus x for our reactants. So if we take the value that is less than 2, you should get x equal to 1.32. Okay, so now that we know what our x value is, we can now write down the concentration of each of the gases at equilibrium. So part C, at equilibrium, the concentration of carbon monoxide is equal to the concentration of H2O, which is equal to 2.00 minus 1.32. And you get 0.68 moles per liter. And then lastly, the concentration of CO2 is equal to the concentration of H2, which is just equal to X. So it's 1.32 moles per liter. Okay, so let's see what the junior tutor wrote. The reaction above is an example of a reversible reaction. At the end of the reaction will reach a state of equilibrium where the rate of the forward and reverse reactions are equal and the concentration of the reactants and products remain constant. Moreover, since the reaction happens in one phase, a homogeneous equilibrium will occur. Part A. Writing the Kc expression, we just need to plug the species into an equilibrium expression. Remember that the numerator is for the products and the denominator is for the reactants. Thus, Kc is equal to CO2 times H2 divided by CO times H2O. B. For the ice table, we need to remember that the concentration of the reactants decreases in the same rate that the concentration of the products increases. This is so because the coefficients of the species are 1. We will denote that amount as X. Okay, so this is what their ice table looked like. And then to calculate for the equilibrium concentrations, we substitute the expressions in row E of the ice table to the Kc expression. Okay, so they showed their work with the quadratic formula. And here they had the X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so you can see here that they got the two different x values. So one of them was greater than 2 and one of them was less than 2. So they said we will choose the second root since we are to substitute the value of x to the expressions in row E of the ice table. Using 4.1 would result in a negative concentration, which is not allowed. Using the 1.32 as the value of x, we get 0.67 molar as the concentration of carbon monoxide and water, and 1.32 molar as the concentration of CO2 and H2 at equilibrium. Yep, so this solution is correct. Okay, so now let's move on to question number 6. What is the conjugate base of NH3? So the conjugate base this is formed when an acid loses a proton. So protons are just H+. Okay, so when we have NH3, and it loses its proton, it becomes NH2 minus plus H plus. So this is an amide, and this is our conjugate base. Okay, so let's see what the junior tutor said. Conjugate base is a substance that is formed when an acid loses a hydrogen ion. Hence, the conjugate base of NH3 is NH2 minus the amide ion. Yep, so this solution is correct. Okay, so on to question 7. What is the formula for the acid and base dissociation constants? Okay, so first let's do the acid dissociation constant. So when we have a general acid, let's just write it as HA. When it is dissociated in water, let me show that this is HA aqueous plus H2O. This makes the hydronium ion, which is H3O plus A minus. Okay, so when we write the expression for the acid dissociation constant, which is Ka, it's going to be the concentration of H3O plus. So basically the concentration of our products divided by reactants. So H3O plus times the concentration of our conjugate base. So in this case, it is A minus. And when we write down the expressions, we only want to include the ions that are aqueous, so water won't be included in the expression. So over the reactants, it's just going to be the concentration of HA. Okay, so this is how you would find the formula for the acid dissociation constant. And now we can do something similar for the base. So let's say we had a base B. When it dissociates in water, it gains a proton and becomes BH plus OH minus. So when we find the Kb expression, it's equal again concentration of products over concentration of reactants. So concentration of BH plus times the concentration of the hydroxide ion divided by the concentration of the base. And that is how you find the Kb expression. So it's important to know how to find these acid and base dissociation constants because this can help us find the pKa and the pKb. So pKa is equal to the negative log of our Ka value, and the pKb is equal to the negative log of our Kb value. Okay, so let's see what the junior tutor said. Kb is the base dissociation constant. So they started off with the base first. This is a measure of how completely a base dissociates into its component ions in water. For a general chemical equation, B plus H2O makes BH plus OH minus. The formula for Kb is written as Kb is equal to the concentration of BH plus multiplied by OH minus divided by the concentration of B, where the concentration of B plus and OH is the concentration of the dissociated ions. On the other hand, the acid ionization constant, Ka, is the equilibrium constant for chemical reactions involving weak acids in an aqueous solution. The numerical value of the constant is used to predict the extent of acid dissociation. A larger value of the constant means stronger acid, and a small value indicates a weaker acid. For a general chemical equation of the form Ha plus H2O makes H3O plus A minus, Ka is expressed as the concentration of H3O plus times the conjugate base, which is A minus, divided by the concentration of the acid, where Ha is the undissociated acid and A minus is the conjugate base of the acid. Yep, so this solution is correct. Okay, so I think that is all the time that we have for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also don't forget to leave a like and a comment if you enjoyed today's video. And also you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.